Okay, so nothing, you know, I don't know what quite to take away from this, but I wanted to tell you that this has been done. I would say that Esslinger has also done experiments with kind of 2D disordered bulk gases. There's no lattice present, they're just atoms running around in some kind of disorder. And he's mostly been able to see diffusion and classical trapping phenomena in his experiments. So I'd say 2D localization for bosons or for Anderson localization, I'm not sure it's really been seen. Okay, so a very recent measurement I want to tell you about is manual blocks measurement, which is an exciting measurement. So I mentioned this one yesterday. This is bosons. Now this is 2D with a lattice. So you should think about this as 2D Bose-Hubbard, where a lattice is formed for atoms trapped in a plane. And this is an experiment where localization of some kind was seen, I think. So there's trapped in a plane here. There's an optical lattice superimposed on it, so a square lattice in this plane. And this is a projected disorder experiment, where it's kind of like controllable speckle. So they controlled it to have some determined disorder potential on top of the atoms, which you can kind of see there. And they generated a Gaussian distribution of disorder site energies. So this is the model they realized. So this is 2D disordered Bose-Hubbard model, where the disorder is mostly in the site energies. Atoms are trapped present. So what they did in this experiment was they started with a mod insulator and they tried to heat it by a lattice quench. And then what they did was they did an experiment where they removed atoms from half the gas. So here's kind of an in situ density profile they measured, where, you know, it's a gas, it's in the trap with a disorder present, and there should be a whole blob here, kind of like what you see here. But this is a case where they, through some AMO magic, blasted away half of that gas, so there's like an edge of the gas now. And then they watched that system relax. So this is a relaxation measurement aimed at trying to observe MBL. And here are data, and you can see what happens over time. This is out to 200 tunneling times or so, 250 tunneling times, is that the gas slowly relaxes back into being a blob in the trap and having kind of a Gaussian-ish density profile, which it should. And that was matched to theory on this side. Oh no, that's an average image, sorry. This is a single shot of the experiment. This is not theory. Single shot of the experiment, and this is averaged over many, many runs of the experiment. So you can see more clearly what's happening here. Okay, does that make sense, what was going on? Okay, so on this side, this is with a whole bunch of disorder. Okay, here's a single run of the experiment. This is average over the experiment. And here you can see the system is not fully relaxing. In fact, it has a density imbalance across the center of the trap, which lies right here in the middle of this circle. Okay, so then what they did is they measured this. They did a lot of things in this paper. I'll tell you just about a little bit of it. You can go read the paper. They measured the imbalance here. So the imbalance in density across the center line here, which is the center of the trap. Right, if the system thermalized and relaxed fully, that imbalance should be 0, which is basically what's happening here. Okay, so here's some of the data they took. This is with no disorder, the green points. You can see the system relaxes back to equilibrium, where the density profile is symmetric across the trap. And this is with increasing amounts of disorder. This is lots of disorder. And so what was observed here is the system does not seem to relax on this time scale. Okay? And so there was a claim in this paper that this is a realization of many-body localization. This inability to relax, and this disordered Bose-Hubbard model. Okay, so that's one claim of MBL, and I'll show you sort of two other ones in cold atom experiments. Yeah?
What exactly is the last?
Yeah, so what they did here was they changed, they start with a cold gas, okay? Condensed a BC. They turn on the lattice slowly, which is usually what we do in these experiments, right? Up into the regime where they have a mod insulator. Right? The tunneling time is very slow, and it's an insulator. Then what they did is they quickly, faster than all their time scales, shut it down to restore tunneling. And in principle, what this does is this kind of adds energy or heat into the system. In practice, there have been groups like my group and other groups have shown that this is kind of complicated what this does, and it's not clear that that's really what's necessarily occurring. But that was kind of the idea here. So the idea here is they try to start with some kind of hot-ish mod insulator, and then watch that system relax. Any other questions about this? This is an important experiment which was just published. This is a paper you shall read and think about, see what you think about it. Yes?
Wouldn't there also be a possibility
Yeah, so in all these AMO experiments, tunneling aside from nearest neighbors is really, really small. It's down by 2 orders of magnitude compared to the nearest neighbor tunneling.
But that would also depend on the process.
Yeah, so for any reasonable lattice potential depth, even for relatively low lattices, that tunneling to next nearest neighbors is really strongly suppressed. Now, on this time scale, it might be playing some role. I'm not actually sure. Although I suspect not. Pardon me? I'm sorry, I'm having trouble. Yeah, so David Hughes did theory on this and exactly diagonalized the disordered system, but not interacting, right? You can't, so this model is not particularly solvable. You can, so to back up, okay, so the ground state of this model we know. All right, so with a big computer, quantum Monte Carlo, 2D Bose-Hubbard, we know the ground state phase diagram. We also know a little bit about, okay, so someone has to go calculate it. I'm not sure it's been done here. We know a little bit about what happens at low temperatures. So for example, Ishnish-Ray did this for our experiment in 3D. Right? At the temperature ranges they were attempting to sample here, the phase diagram is not calculable as far as I know. They won't have a big enough computer to do it. Okay, and no matter what, for any time scale, for any temperature range, the dynamics are not calculable. It's an unsolvable problem right now, unless someone smart figures out some analytical approach. And to be careful though, let me just say that there are approximations, and there's a paper out by Scarola and Marcus Riegel now, which has a different interpretation of these data, where they use a time-dependent Gritzfiller to solve what's happening. Okay, and that's an approximate method, not an exact method. Yeah? Yeah. So I encourage you to read that paper too, and to think about what you think is going on here. Yep. But that of course is approximation. Solving this exactly, the dynamics, or quite away from zero temperature, is not a thing we can do at the moment. It's exciting, actually. Yeah, question?
What were those authors?
So those authors' names are Riegel and Scarola. This paper's on the archive. It's not been published yet, but Marcus Riegel is at Penn State University, and he's been actually really done a lot of the foundational work in understanding thermalization in closed quantum systems. And Peter Scarola is at Virginia Tech. So they've got a paper in the archive, which offers an alternative interpretation of this, and I think, you know, whatever's happening here, the experiment's very interesting, all right? And there's plenty to be learned here, and plenty more measurements to do, include what happens at longer times and higher disorder strength, and that'll all be exciting to explore. Okay, so this is one claim of MBL. This would be MBL on 2D. Okay, I might go a little bit past 10:45 to tell you about some other stuff, but I'll try to skip through things maybe you find less exciting. All right. Okay, so maybe I'll skip through some of my own work. You know, we have also looked at the disordered Bose-Hubbard model in 3D, okay? And I told you kind of how this experiment worked yesterday, where we combined speckle fields with a cubic lattice, okay? And my group does experiments in this 3D disordered lattice with rubidium-87 atoms, which are bosons. And so we realized this disordered Bose-Hubbard model, I told you about it yesterday, where there's disorder in every parameter, and there's a track present, which I should have written in here. So you can go read a bunch of our papers on this. So one thing we've been able to see in this experiment is a transition between a conductor and an insulator through transport measurements. We are able to see actually a superfluid turn into entirely a Bose glass, measurements published in 2010, and you can go learn more about that. There's also a recent paper we have published in Nature Physics on a disorder quench. We're able to see through a quench measurement where we quench the disorder dynamically in time, this same kind of transition from a superfluid to a Bose glass. Okay, so let me skip ahead to other people's papers. You know, again, how this is related to MBL, I don't really know. This is more like low temperature, but still non-zero temperature physics, looking at localization. That's what I want you to take away from this. And then you should just go read the papers and bother me through email. Okay. So the reason I'm going to skip this is let me get on to two of the other claims of MBL-related phenomena. So since that's kind of the topic of this thing, let me do that without going too far over my time. Okay, so then I'll tell you about two other measurements, I guess. And these are measurements with disordered fermions. Okay, so far I was talking about Anderson localization, which probably doesn't care too much about the quantum statistics. I told you about dirty bosons, which definitely cares about the quantum statistics. And now I'm going to tell you about dirty or disordered fermions. I'll tell you about a couple experiments here where claims of MBL were made. And then you can go read more about it, bother me through email, and bother the authors of these papers. So this was a paper from Manuel Bloch's group, kind of really Uli Schneider's group, where they trapped two hyperfine states of potassium-40 atoms. So don't read Java, because then we'll work with another thing. So thanks for asking. Okay. Let me make sure the remote works. Okay. So here what they did was they used fermions, potassium-40, they used two spin states, called them spin up and spin down, that's fine. And they did an experiment with an incommensurate lattice. Okay, so they had an incommensurate lattice present. So here's just their incommensurate lattice formed in the way I've been telling you about. So the Hamiltonian, they realized is kind of this interacting Aubrey and Drake Hamiltonian again, which is maybe written down in kind of a sloppy fashion, where there's spin present now, you have to keep track of the spin. So each spin state can tunnel through the lattice. They experience disorder from the incommensurate lattice, which is present. That's this term that looks like a site energy shift in this approximation. And if two atoms, one spin up and one spin down on the same site, they can interact with each other through an interaction energy U. And there's also a track present. Does that make sense? What they're doing? Okay, so I'm not going to go into a lot of detail. We don't have time. Let me tell you what the basic measurement they did. The basic measurement they did, again, through some AMO magic, just assume that, was they prepared kind of a charge density wave in the lattice. So what they did was they prepared an initial state where they have sites that are occupied, unoccupied, occupied, unoccupied, occupied, unoccupied. And then they measured the relaxation of this state. So here's some of their data. So now the imbalance they're plotting is the imbalance in density between these sites. Okay, label them even odd. So it's an imbalance in density, right? So this has a high imbalance, so you could call it 1, all right, in some units, it lies up here. And if the system relaxes, of course, this is not an equilibrium state. If the system relaxes, the particles will tunnel around and spread themselves out, and if it can relax, this imbalance will drop down to 0, and the sites will be equally occupied. So here you can see data taken measuring this imbalance versus time in tunneling times of the main lattice after they prepared this initial state. Okay, so you can see for the non-disordered case, very quickly, this imbalance vanishes and the system is relaxed. As they increase the disorder, what you'll see is that there's some short time dynamics, but for enough disorder, the system does not relax, and you end up with an imbalance in density between these even and odd sites that persists out to long times. And I'm sorry, you can't see these points very well, but there's a bunch of points that live up here on top of a theory curve, and one reason there's an advantage in using this incommensurate lattice is a lot of things are calculable, so they're able to calculate what should happen here and put theory curves on top of this. So here's a plot of that imbalance versus disorder strength, okay? And for this Aubrey and Drake model, for the non-interacting case, there's this transition of delta over J equals 2, and there's a kind of light blue theory curve you can't see very well here. They did more sophisticated theory, including the trap, that's this red line. And these points are the imbalance they measure versus disorder strength. So the imbalance out here at long times versus disorder, no imbalance, it's at the point. This point is over here somewhere, and this point is over here somewhere, and this is the imbalance they measure. And there was a claim in this paper that this was also a measurement of MBL. Okay, so I'll tell you about, I know my time is up, I'll tell you about one more measurement. Again, it's my measurement. So there's that. My measurement, so we also did experiments with a 3D disordered lattice with fermions. Okay, so in this case, we did a measurement of a disordered Fermi-Hubbard model. And that's a model we realized. Let me just skip through this quickly. We did a transport measurement where we measured something like the conductivity versus disorder strength for different lattice steps. Okay, and I'll just flashed all this data. You can go read the paper on your own. So we measure that. We measure the amount of disorder required to produce an insulating state, okay? And, which means no conductivity. We can only see a transition to that kind of state occur. And we can make a phase diagram where we look at that amount of disorder versus interaction strength. And we see this as insulator metal transition, and the interactions affect that, shift that to higher disorder. And then we also can see that that insulating state is robust against temperature, so we can turn up the temperature and that insulating state stays insulating. And so our claim was that this was consistent with all the predictions from the Basco, Liner, Altschuler paper and the perturbative limit of this model for many body localization. So that's kind of the third claim, or we were very careful to say it's consistent with the predictions in this paper, and that's the third paper you can go read. So you should go read this paper too and learn more about it. Okay, so that's all I wanted to talk about. Those are all the kinds of things I told you about. I didn't go into any detail, but I'll make these slides available to you, and you can go look up all these references and learn more yourself. Okay, that's it.
Supposed to be the end of Professor DeMarco's 3 lectures. Yep. We have prepared small gift for you. So
right.
Thank you for your excellent lectures.
All right, thank you.
That's our guest.
Thank you. Okay, so as I mentioned, I have to go drive to the Philadelphia airport now, so I have to make a hasty exit. But you can contact me through email. I'm always glad to talk about stuff. You may send me an email and I may not respond for a while. I'm kind of a typical professor, but just keep bothering me. I won't feel bad if you keep bothering me. So, see you around.